Hello friends, I am Samir and I welcome you all to your own YouTube channel Aryabhatta. Friends, today our topic of discussion is adjoint or adjugate of a square matrix. So, in this video we are going to learn that what is the definition of the adjoint of a square matrix and how to find it out and what are the different properties that belongs to the adjoint of a square matrix. So, to discuss further, let us take a square matrix A which is of order n and let the representative element of this square matrix A is A.adjA, where you know I represents the row number and j represents the column number. And together with that, let us take Cij as the cofactor of the element Aij in the determinant of the matrix A. I am representing C of A as the cofactor matrix obtained by replacing the element Aij of the matrix A with its own cofactor Cij. Let us try to understand this through one example, friends. I am taking a 3 by 3 order square matrix A whose elements are A11, A12, A13 and so on, as you can see. So, the cofactor of the element A11 you can calculate by its formula and let by symbol it is C11. So, the cofactor of A11 is C11. So, what I will do now? I will replace this element A11 with its own cofactor C11 and the same thing I will do for each and every element. I will replace A12, the element A12 by its cofactor C12. So, by doing this and by replacing every elements by their own cofactors, I am getting a new matrix of only cofactors, where the elements are cofactors. That I am symbolizing as C of A, cofactor matrix obtained from the matrix A. So, friends, now come to the definition or formula of the adjoint of a matrix. So, the adjoint of a square matrix A is nothing but the transpose of the cofactor matrix of the matrix A. That means, here after getting the cofactor matrix of the matrix A, the adjoint of A will be the transpose of the cofactor matrix of A. That means, find out, you have to just find out the transpose of this cofactor matrix of A. That means, we have to make the rows to its respective columns. Row 1 will become column 1, row 2 will become column 2 and row 3 will become column 3. In that way, we are getting the adjoint of a matrix. So, the adjoint of a matrix, its formula and calculation is very simple. So, friends, let us try to discuss this through one example. The question is to find out the adjoint of the given 3 by 3 square matrix, where the elements are 1 1 1, 2 1 2 and 1 3 1 row wise. So, first let us name this matrix by the letter A, which is a 3 by 3 order matrix, which representative elements are A, ij and Cij and Mij are respectively the cofactor and the minor of the element Aij. So, friends, here C11 is the cofactor of the element A11. A11 means the element at the position of first row and first column. So, here the first row and first column element is 1. So, our A11 is, the value of A11 is 1. Now, the cofactor of this element 1 is equals to minus 1 to the power 1 plus 1. This 1 plus 1 is taken from here, row and column number sum, into the minor of that element, which is M11, and M11 the minor is obtained by removing its own row and column. So, if you remove the first row and first column, then you are getting the determinant of 1 2 and 3 1, that is the minor. So, minus 1 to the power 1 plus 1 is positive and the minor is this, and after calculating this determinant you are getting the value of C11 as minus 5. Similarly, we will find out all the cofactors of each and every element present in the matrix. Now, after getting the cofactors, we will arrange them in their own positions of the original elements, and by that we are getting the cofactor matrix of A like this. Now, the adjoint of that matrix A is the transpose of this cofactor matrix. So, the transpose of this matrix is by changing the rows to respective columns, you are getting this. So, calculating the adjoint of a matrix is very simple, which will help you in further calculation of inverse and many other things that are coming in our videos to discuss. So, friends, now come to the properties of adjoint of a square matrix. For that, let us take A and B, which are two square matrices of same order n. Then the first property says that if you are multiplying a matrix with its adjoint in any order, that means product of A into its own adjoint of A is equals to adjoint of A into A. That means it is commutative. Generally, matrix multiplication is not commutative, but here the multiplication of a matrix with its own adjoint matrix is commutative, and that is equals to a particular type of scalar matrix. So, by scalar matrix, I am telling that you know what is the scalar matrix definition. Scalar matrix is a diagonal matrix whose main diagonal elements are all equal. But here it is a special type of scalar matrix, because that diagonal element here is nothing but the determinant of that matrix of which we are multiplying the adjoint with it. So, friends, we can prove this one also. Let us take a matrix A, which is of n by n order with representative element A.adjA. Now, the element on the ith row and jth column of the product of A with its adjoint is represented as A_i1 into Cj1 plus A_i2 into Cj2, and in this way it is ending at A_in into Cjn, where A_i1 represents the element in the ith row and first column, and it is multiplied with the cofactor of the jth row and the first column, and that all we are adding together. Now, this product of elements and some cofactors will lead to two type of values. Either you will get the determinant of that matrix as the result, or you will get 0 as the result. This sum, this total sum may be either 0 or equals to the determinant of that matrix. It is equals to the determinant of the matrix if that I and j, this row and this column number are equal. This is leads to the Laplace law, where actually we are multiplying the elements of any row or column with its own cofactors, and that leads to the determinant of that value. But if I and j are not equal, if the row of the element, row number of the element and row number of the cofactors are not equal, then we are multiplying the elements of any row with the cofactors of any other row, and that leads to 0, as we know this property before. So, in this way, if I and j are equal, that means it is representing the diagonal elements. That means all the diagonal element products will be equals to a determinant, and if I and j are not equal, that represents the non-diagonal elements which will be 0 in this product. So, if you are multiplying A with its adjoint, you are getting the same order, that means nth order square matrix, where the non-diagonal elements are all 0 and the diagonal elements are all equals to the determinant of A. Now, as determinant of A is common here, we can take it out from the matrix. So, determinant of A if you take out, you are getting one identity matrix of order n, and that I am symbolizing at In. So, in this way we are getting that the product of A with its adjoint is resulting in the product of the determinant of A into identity matrix. Similarly, we can prove that adjoint of A with the matrix A will also result in the same value, determinant of A into identity matrix of order n. So, that means both are same, and we are proving this result in this way. Now, come to the Second property, friends, in the second property it says that adjoint of the transpose of a square matrix is equals to the transpose of the adjoint of that matrix. Third property says that if you are multiplying two matrices of same order A and B and you are finding out the adjoint of it, that means it will be equals to the product of the adjoints of the individual matrices. Fourth property says that if you are multiplying a scalar k with a square matrix A, k is a real number, here the scalar is a real number. If you are multiplying a real scalar number with a square matrix A and you are finding out the adjoint of that product of that matrix with that scalar, then that will be equals to the product of k to the power n minus 1 with the adjoint of that original matrix. Now, here what is n? N is the order of this matrix A. So, that means if you are taking out the scalar k out of the adjoint of that matrix, then that k is coming with the power 1 less than the order of the matrix A. The fifth property says that adjoint of A to the power m is equals to adjoint of A whole to the power m. Sixth property says that adjoint of A, that means if you are finding out 2 time adjoint of a matrix, then that is equals to the determinant of A to the power n minus 2 multiplied with the matrix A, where the determinant should not be 0, that means it should be non-singular, and here as usual n is the order of the matrix A. Now, the adjoint A is determinant value is equals to the n minus 1th power of the determinant of the matrix A, where the same condition holds, determinant should not be 0. And the determinant of the adjoint of A, that means 2 times of adjoint of a matrix you find out and find the determinant of it, that leads to A determinant to the power n minus 1 whole square. So, that square whole square is not of the determinant, but of the power n minus 1, where determinant of A should not be 0 as usual. The ninth and the last property of a discussion is the adjoint of a diagonal matrix is again a diagonal matrix. So, friends, this is all in adjoint of a square matrix for today. Hope you understand this topic. So, keep subscribing and thank you very much for watching this video.